welcome to the next session on quantum computing, Harrow-Hazen-Lloyd algorithm. So in this session we are going to discuss about Harrow-Hazen-Lloyd, and the next thing is about the main components of HHL algorithm and what are the utilization of quantum parallelism and inferences are to be used in HHL algorithm. And next thing is QAOA handle noise and quantum circuits. So what is HHL? So it's a quantum algorithm designed to solve systems of linear equations. It is a simple circuit in quantum computing involves several key components. So we have several steps are there. State preparation. The first one is state preparation. The next is quantum phase estimation. And the third is eigenvalue inversion. Fourth is inverse QPE. And fifth is measurement. In the case of state preparation, the algorithm begins by encoding the vector B of linear system Ax, which is equal to B, in the special quantum state of ket B. In the second quantum phase estimation, we are going to calculate the eigenvalues of the matrix A. It involves applying controlled operation representing A and using quantum Fourier transformer QFT to extract phase information. And the third is eigenvalue inversion. It's a crucial step. We can going to convert the eigenvalues, rotation of ancillary qubits based on the estimated eigenvalues. Then controlled rotation gates are used for this purpose. The fourth one is inverse QPE. The eigenvalue register is uncomputed using inverse of QPE. And the fifth one is measurement. We are going to measure the qubits. A measurement of 1 indicates successful matrix inversion. The main components of HHL algorithm is state preparation. Vector B from the linear system is encoded into quantum state ket B. This involves normalizing B and representing it as a superposition of computational basic states. So ket B, which is equal to sigma I, Bi and ket I. Efficient state preparation is essential and it directly affects the algorithm performance. Quantum phase estimation QPE is used to estimate the eigenvalues of the matrix A, assuming A is a Hermitian and sparse matrix. This steps involves applying controlled unitary operations corresponding to e to the power IAT, where t is the time, and then performing the quantum Fourier transform of 1 qubits to extract the phase information related to the eigenvalues. Next thing is controlled rotation. Using eigenvalues obtained from QPE, we are going to apply the auxiliary qubits. These rotations encode the inverse of eigenvalues 1 by lambda I into quantum state. This step is crucial for solving the linear system as it effectively computes a to the power minus 1b. And the next step is inverse quantum phase estimation. After performing controlled rotation, IQPE uncomputes the eigenvalues register by reserving the QPE. We are going to compute ket x, which is equal to inverse of A and ket B. So the next thing is measurement. The final quantum state is measured to extract information about the solution vector x. While we are going to calculate the HSL does not provide the direct access to all components, it allows for efficient computation of expectation values such as ket x and determinant of m, where m is observable. Summary of the table is here: state preparation, that is the first step, quantum phase estimation, and the next is controlled rotation, the third is inverse QPA, and the last one is measurement. In the case of state preparation, encode the vector B into quantum state. In the quantum phase estimation, extract eigenvalues of matrix A. Controlled rotation, encode 1 by lambda I into quantum state for inversion. Next is inverse QPA, uncomputes eigenvalues to isolate the solution state, and the next thing is measurement. In the case of measurement, retrieves the solution information or expected values. HHL algorithm utilize quantum parallelism exactly. So quantum parallelism in HHL, the quantum parallelism refers to the ability of a quantum state to process multiple computational paths simultaneously, and the state preparation with the help of a sigma I, Bi, get I, and the next is quantum phase estimation with the help of e to the power minus I, and determinant of ui and get ui to be calculated, where lambda I are the eigenvalues of A. This step process all eigenstates simultaneously. The third is controlled rotation. So once eigenvalues are estimated, controlled rotations are applied based on these values. The quantum system processes all the eigen and eigen pair of vectors in parallel manner. Next is quantum inferences. Quantum inferences is used to combine computational paths constructively and destructively. The next thing is eigenvalues inversion. Controlled rotation encode the inverse of eigenvalues into quantum state. The amplitude of the different paths interface constructively and destructively during this step. And finally, we are going to calculate inversion quantum phase estimation IQPA after controlled rotation. IQPA reverse the QPEA process, and we can easily interface to decide the unwanted components within the isolated solution. So efficiency through parallelism and interferences. So here is we are going with the final summary. In HHL, quantum parallelism enables simultaneous processing of all the eigenstates during QPE and controlled rotation, while quantum inferences ensures that only the correct solution emerges after IQPE. Together, these principles allow HHL to solve sparse linear systems with low conditional numbers exponentially faster than classical methods under ideal conditions. The next thing is QAOA handle noise in quantum circuits. Quantum approximation optimization algorithm is sensitive to noise in quantum circuits. So we need to go with that, optimize the circuit depth. So trade-off between depth and noise. So the number of QAOA layers improves the algorithm expressive and accuracy also. For example, show that for a certain 5 qubits problems, accuracy increases up to 6 layers but declines with further depth due to the noise accumulation. Shallow circuits is also there to mitigate noise. Shallow circuits are often preferred to reduce the decoherence and gates on the errors. Second one is classical optimizer selection. Robust optimizer. Classical optimizer like simultaneous stochastic approximation and other kind of approximation algorithm to perform well under short noise and realistic device noise. These optimizers are very good in cost function evaluation caused by noisy quantum measurements. Noise aware optimization. So in optimization process to noise environment, these optimizers help QAOA convergence effectively even in the presence of impurification. Third is variance of QAQO. Multi-angle QAQO is there. Dynamic adaptive QAQO is there. In the case of multi-angle QAQO, it introduces classical parameters per layer, allowing finer control over optimization while reducing circuit path. In the case of dynamic adaptive QAQO, we can go with dynamically adjust the circuit parameters or layer configuration based on the real-time feedback from the noisy device. The fourth one is noise directed techniques. In that NDAR, noise as a resources by iteratively adapting the cost function Hamiltonian to align with the noise dynamics. This approach runs on certain types of noise into an advantages, improving quality of the solution in the noise environment. Next is simulation and calibration. Here also we are going to identify optimal circuit parameters and configuration for specific device. For example, in IBM itself, we have a Bellman's noise model is there insights into the optimal layer depths and optimizing the choices. Last one is about the hardware improvement. While not intrinsic to QAQ itself, advancement in quantum hardware such as error correction techniques are improved in qubits coherence times. directly affect the QAO by reducing overall noise levels. So the recent implementation is improved circuit implementation have to be verified using IBM Qiskit, and the experimental demonstration also to be embedded in quantum system model H series trapped quantum computers. So in the implementation challenges, resource requirement is also to be biggest task, and hybrid approaches also to be very biggest task. And circuit compression, spectral scaling, error mitigation. These are the important challenges and improvement we are going to go with the quantum computing. Thank you, learners. We will see in the next session.